How a battery really works. All right, let's get into it. You use them every single day, right? In your phone, your remote, maybe even your car. They're these quiet little boxes of power we totally take for granted. But have you ever actually stopped to wonder what is going on inside one? Well, we're about to find out. I mean, that's the real question, isn't it? How does this little thing, this simple object, hold enough juice to run the incredibly complex gadgets that basically define our lives? Well, I'll tell you, it's not magic, it's chemistry, and honestly, it is absolutely fascinating. So to really understand this, we've got to metaphorically crack open the case and see what's inside. And it turns out pretty much every battery, doesn't matter if it's a tiny watch battery or a huge one for an electric car, is built around the same three key players. Okay, so at the very heart of the battery, you've got these two opposing forces. On one side, there's the anode. Let's just call it the giver. Its whole chemical purpose in life is to get rid of electrons. Then on the other side, you've got the cathode, the taker, and you guessed it, it is just desperate to grab those electrons. This fundamental tension, this push and pull, is where all the power comes from. Look, we're not talking about some weird abstract stuff here. These are real tangible materials for the anodes, the givers. You're often looking at elements like zinc or graphite, or the real rock star of modern batteries, lithium. And for the takers, the cathodes, chemists use compounds with stuff like manganese, cobalt, or nickel. The specific combo of these materials is what actually determines how powerful the battery is. So you might be wondering, if the anode wants to give electrons straight to the cathode, what's stocking it? Aha! This is where our third key player comes in, the electrolyte. Think of it like a super specific bouncer at a club. It lets certain things pass through, in this case, charged atoms called ions, and this right here is the secret sauce. It completely blocks the electrons from taking a direct path. It forces them to go the long way around. Alright, so we've met our players. Now let's zoom way in and watch the process that makes it all happen. This is the chemical reaction, this atomic dance that is the real engine of the battery. Okay, quick sidebar for a super important term. We need to know when an atom over at the anode gives away one of its negatively charged electrons. It's now left with a positive charge. It's not a neutral atom anymore. It's become an ion. This little guy is going to be key to what happens next. So here's how the dance goes in 3 steps. First, at the anode, you get a process called oxidation. That's just the fancy science word for the anode, giving away its electrons. Now those newly created positive ions, they can travel right through that electrolyte gatekeeper. Meanwhile, the electrons that just gave up are now stuck, desperate to get to the cathode, which is just waiting to accept them in a process called reduction. And the reason this whole thing happens is actually pretty simple. Nature just loves balance. Chemistry is all about finding a stable, balanced state. The anode has way too many electrons it wants to ditch, and the cathode has a big deficit it wants to fill by connecting them with a wire on the outside. We're literally just giving those electrons a path home. Okay, that's the microscopic chemical reaction. It's pretty cool. But how do we get from that tiny atomic dance to, your phone screen lighting up? Let's zoom back out and connect the dots. So remember how the electrolyte forced those electrons to take the long way around? Well, that long way is what we call a circuit. When you pop a battery into a device and flip the switch, you're creating that closed loop. You're completing the path for those electrons to finally travel from the anode through your device and get home to the cathode. Here it is. This is the punchline, that flow, that massive journey of countless electrons all rushing from the negative terminal to the positive terminal through all the tiny wires in your device. That is electricity. The work they do along the way, that's what powers our entire world. But this whole elegant system relies on that path being very specific and very controlled. So what happens when that path gets broken, or even worse, when the electrons find an uncontrolled shortcut? First, let's look at the simple case. A complete or closed circuit is a happy working circuit. The electrons are flowing, your flashlight turns on. But if you create a break in that loop, which is all a switch does, it becomes an open circuit. The path's broken, the electrons stop, and the light goes off. Simple as that. Now for the dangerous one. A normal circuit has things in it like a light bulb filament that provide resistance. Think of it like friction for electricity. It slows down the electrons and keeps the flow at a safe, manageable level. A short circuit is what happens when those electrons find a dangerous detour, a path with almost no resistance at all. A really simple bit of physics called Ohm's law shows us exactly why this is so incredibly dangerous. It's a formula that says the flow of electrons. The current is equal to the battery's voltage divided by the circuit's resistance. In a short circuit, that resistance value, the R on the bottom of the formula, suddenly plummets to basically zero. So what happens in math when you divide by a number that's practically zero? The result gets insanely huge. The current just skyrockets, the floodgates burst open, and all of the battery's stored energy gets unleashed all at once, and the consequences of that electrical flood are, well, they're not good. The massive current makes wires glow red hot almost instantly. The battery's chemical energy gets dumped in a split second, and all that intense heat can easily lead to a fire or even a pretty serious explosion. So when you strip away all the complexity, that's what a battery really is. It's not some bucket you fill with electricity. It's a brilliant device for creating a perfectly controlled chemical reaction, one that's designed to release its energy slowly, safely, and usefully, which kind of leaves us with a final thought to chew on. We are always pushing this technology to its limits, right? We want more and more power crammed into smaller and smaller packages. So the real question for the future is, as we keep shrinking this incredibly powerful chemical dance, how do we innovate to make absolutely sure it always stays controlled, balanced, and most importantly, safe?